Ah, we have audio.
Thank you all very much for getting up this early in the morning. I certainly fought pretty hard. Today I will be talking about detecting stereographic content on the internet. And this is work done at the Center for Information Technology and Innovation at the University of Michigan. I was speaking 4 years ago at HIP using hand-drawn transparencies, which was really high assurance, but not much very fun. So today I will try to use like a computer with my slides, so we'll see how it goes. My talk is organized as follows. I'll briefly motivate why I'm looking for hidden messages on the internet at all. Then I will start to explain a bit how information hiding works, especially how you can hide information in JPEG images. And then I will continue explaining how you can use statistical analysis to actually detect to some degree if somebody tries to hide information in JPEG images. I'll give you an overview of existing systems that use JPEG images for information hiding, and then I will present a detection framework that I developed to efficiently get like all the images of the internet and find out hidden information. And then I will discuss my results. And finally, so steganography is all about hiding information, hiding that communication is happening. We can categorize it in two different areas. One is watermarking, which is being mostly used for commercial purposes. This is information hiding where the recipient of the data might very well know that information is hidden, but he should not be able by any means to remove that hidden information. He should not be able to destroy that. Well, he should not be able to destroy that watermark without also destroying the content that it's hidden. Information hiding is slightly different. For information hiding, you do not want, speak louder. For information hiding, you do not want an eavesdropper to be able to know that something is hidden within the data that you are sending. So you can use that for communication in such a way that an eavesdropper doesn't really know that you communicate. Both watermarking and information hiding has been summarized by the journal steganography. So in February this year, there was an article in the USA Today talking about evil terrorists they named Osama bin Laden using steganography to secretly communicate with their evil friends in the States to organize some plots. We don't really know what that might be. But they said that they use images on the internet as communication media. And this article was fairly vague. Not much of the information was substantiated in any way. So I was sort of curious on, well, they're saying people are hiding information on the internet, but is it really true? And if that is true, how would they know that it's true? So what can I do to actually verify that? So I started to think about that briefly, and immediately there were three questions that needed to be answered before I could even start answering the question of the newspaper article was true. And one of them is, how do you even detect steganographic content automatically in images? And if you can do that, well, how would you get the right images to detect the information? And then even if you think that you might have detected hidden information, how do you really make sure that there was hidden information? And I will try to answer these questions in this talk, and we'll see what they're going. So to give you some background about steganography. Until a few years ago, all steganography was classical steganography. That means the security of the steganographic system relied on the secrecy of the encoding system. We have a very famous example in history where a Roman general wanted to communicate some information, and he took a slave and shaved the hair with a tattoo with the hidden message on the shaved head and waited for the hair to grow back, and then some slave is around. And since nobody knew that you could hide information on a shaved head, that runner came through and was able to deliver the message without anybody knowing that there was a message being delivered. However, once you know that you can put a tattoo on a shaved head, you can just like take everybody walking by, shave the head, and see if there's something written. So once the encoding system has become public, there's no security in the scheme anymore. And the same is true for other things like using a letter, and every last word in the letter spells out the hidden message. For images, just take the least significant thing to hide your message. Well, for modern steganography, this should be different. Modern steganography should only be detectable if some secret information is known. And in most cases, that's a secret key, a passphrase, something that you need to know in order to retrieve a message, in order to even tell that there's a message. And this is sort of similar to cryptography, where you have the cutoff principle that says of the security to just rely on the activity. So you want the same for steganography. Steganography should only be detectable if you know the right key, and all the security of the scheme should be. Well, nonetheless, since all these schemes modify the data that you try to hide information in slightly, they leave detectable traces. And if you're able to find a way to point out these discrepancies, you're able to tell that information was hidden, you're able to break this pattern. So while the secrecy of the information is not degraded, you might be able to tell that there's something hidden. You do not know what has been hidden. The purpose of steganography is to defeat it, because you try to make it impossible for anybody but the recipient to know that information was hidden to begin with. You don't want anybody else to know that communication is hidden. Well, I'll explain how the information hiding process works in general. You have some digital data object, and from that object you can identify redundant bits. These redundant bits are bits that you can modify without degrading the quality of that object. So, example, if you take an audio file, you might be able to twiddle with the least significant bits, and the human ear will not hear it. The same is true for image files. You can twiddle with least significant bits there, and an eye will not be able to tell the difference. However, the most significant bits, these will, if you modify them, show immediately in the image, and those would not be redundant. So the redundant bits are all these that you can modify without degrading. Well, now the system selects a subset of these redundant bits to replace them with the bits of the message that you want to write. And the way you do that can be all different ways. This applies both to classical and modern steganography. And then finally, once you have selected the subset and put your message in there, you put everything together again and create it, and put it in the cover medium to create the stable medium that you'll finally use to transmit or put somewhere. And in this case, you can destroy the cover medium. The recipient doesn't need to know the cover medium in order to get your message. The stable medium itself is sufficient. However, since you replace redundant bits with your message bits, you modify them. You modify the redundant bits. And this can change the statistical properties of the cover medium. And if you know the statistical properties, and you see that they don't really fit with what you expect anymore, then that's a way to tell that information is being. So, how does information hiding work in JPEG images? Well, for JPEG images, you use a discrete cosine transform. That means you transform from pixel space to a frequency space. And in JPEG, you take an 8 by 8 pixel block. And the result of the discrete cosine transform are 64 frequency coefficients. And one thing to note here is that if you modify one of these coefficients, all 64 image pixels will be modified in some way. So your modifications are sort of spread out. And the redundant bits in the case of the JPEG image format are the least significant bits of the quantized DCT coefficients that we get from the discrete cosine transform. So because the changes to the coefficients are sort of spread out, there are no known visual attacks against JPEG. And with visual attacks, we mean, For example, you take an image of a house. If you look at the image, you see the structure of the house. And you also notice that the structure of this house is sort of preserved in all layers of the image. So if you strip off the most significant bits, you still see sort of the structure of that house with the least significant bits. And there are many schemes that do steganography for JIT images that just overwrite the least significant bits without doing anything. And then if you look at such an image, you see that the structure of this house has been destroyed where the message has been hidden. So if you just do it from the beginning of the image, you might see that half of the image in the least significant bits suddenly looks random, and the rest still shows the structure of the house. And that would be a good. So now, for example, I've taken an image of my friend Arthur visiting me in the States with a bird on a set and his favorite operating system on shirt. And then I took a text of Lewis Carroll, Hunting of the Snow. Actually, I only took the first chapter because it's so long. And hid it in the JPEG image, and this is the result. If you look at it very closely, you'll not be able to see any difference, because there is no difference in the human eye. However, things have been changed, statistical properties might have been violated. So even though the human eye doesn't see anything, there might still be a way for statistical analysis to determine that steganographic content is blind. So if you can define a statistical test that reveals that information has been hidden, you destroy the steganographic system. So what tests would we think of? Well, very simple tests would just look at the entropy of the redundant bits. So assume you have an encrypted message. You put that in the redundant bits. Because the encrypted message is a very high entropy, you will notice that the redundant bits have a higher entropy. A simple test could be the correlation towards 1. You count the number of 0 bits, you count the number of 1 bits. And before you might have 70% 1 bits. After you put in the hidden message, you suddenly might only have 60% 1 bits. So you get closer to a higher entropy. Or you can use Amara's universal statistical test for redundant bit generators, which will give you a better quantification of the numbers. However, after hiding data, we expect something to change. And these tests, as I said, are very simple, so they will not be able to give us a yes or no decision to determine if information is true. From that, we need to get the bit system. So Westfeld and Fitzman observed that the embedding of encrypted data changes the histogram of color frequencies. As I just said, encrypted data is a high entropy. 0 and 1s are equally likely to happen. And now if you think of an image that has the color 2 in there quite often, and the color 3 only a few times. First of all, you have to notice that 2 and 3 only differ in their least significant. So if I just modify least significant bits, and I put a 1 bit into a 2, it will become a 3. And if I put the 0 bit into a 3, it will become a 2. Since the data is encrypted, both 0s and 1s are equally likely. And if you have many 2s, you'll find that quite often you change them to a 3. But you only have a few 3s. So only very rarely you change a 3 to a 2. And before you hit the information, you have many, many 2s and only a few 3s. And after you hit the information, you'll find that the frequency of 2 and 3 are very close together. Because you change the 2 so often to the 3, you gain many 3s, but you only lose a few 3s and get a few 2s. So after hiding the information, the frequency of the JSON colors is similar. And the same is true for the JPEG image form. Instead of taking colors, or the frequency of the colors, we take the frequency of the DCT coefficient system. And let's see how that works. We have seen this graph here. The first graph shows us the histogram of the DCT coefficients before modification, and the second graph shows us after modification. And we'll be looking at the -1 and a -2. And we notice this is very frequent, that after hiding information, it sort of goes down a bit. And the -2 is not that frequent, but because the ones get changed, the -1s get changed more often to a -2, we'll see that this goes down. And it's sort of becomes similar. Well, this is the result. We see it there, come closer to that. And here you see the difference. Wonderful. So, and this is something, yes? Oh, I'm sorry. So, and this is something that we can test for. We can define a statistical test that will tell us if an image has a histogram distribution where adjacent coefficients have similar frequencies. And one test to do that is the chi-square test. This allows us to compare the two distributions with another, and then we can derive the probability that these two distributions match. And the one distribution that we take is the DCT frequency distribution that we find in the image as we do have it. And the distribution that we test against is the distribution of the same image where we take the average of these adjacent coefficients. And taking the average essentially means that adjacent coefficients have the same frequency. And then we can calculate the probability that these coefficients have been changed by a steganographic process at every point of the image. And the graph below is sort of an example of that. I took this chi-square test, and I took parts of the image and calculated the probability. But we are looking at the distorted frequency distribution. But we are looking at an image that has hidden information. And here you see the probability that this is true. And normally you'd expect, well, you know, if hidden information is in there, and we have a statistical test that tells us information is in there, then we would always expect 100% match. That's what the test should do. Well, that's not how it quite works, because, as I said, we frequently change one coefficient to the other, but we don't really modify so many that the frequencies will become the same. So you just find some kind of closeness. Here we get like 60% probability that information is being hidden. Here it's 90. And so we have to find a way to make this into a decision if information is hidden. And I'll show you how.
How
Yes.
does it looks like when you have an image that doesn't have any?
Oh, in this case, it was an image that had something in there. I'll come back to that very shortly, and you'll see exactly what I mean. So we'll get statistical distortions. These distortions actually depend on the system that has been used. Because every system is a different way of selecting these redundant bits. Every system takes a different subset and does something. And now we can see that the type of distortion actually identifies the system that is being used. And I'll explain to you how the most common systems work. So the first system, and I think that was in 1994, is JSTAC. And that's very simple. There's a Windows user interface, JSTAC shell, that gives you some fancy encryption and compression. And that is the technical statistical analysis. And there's something called JP-Hide, which is a Windows interface too. It was just tested. It's very good in a German magazine a month ago. But that is the technical part of statistical analysis too. And then there's a program that I wrote a couple of years ago, Outguess. That is the technical statistical analysis too. However, since I've done this work, I also figured out how to make things undetectable. So the new version of Outguess is not detectable. And it doesn't mean that it's 100% secure, but it's better than what there was before. So let's look at JSTAC. JSTAC is a patch to the JSTAC library, and it's just a command line interface, not very convenient. And the DCT coefficients of the JPEG image are modified continuously from the beginning. So there's no randomness involved in this process at all. And there's no encryption. And since there's no encryption, we don't have this property of equal zeros and ones. And in this case, I embedded hunting of the snark compressed by EZ2. And you know, compression is high entropy, so it's similar to encryption. But if you look at this graph, you'll see that there's a very low probability of embedding at the beginning. And that is because EZ stores a dictionary at the beginning, which is not going to be good. And afterwards, you'll see a very nice correlation that tells us something is being hidden. And that's a way to detect that an image is being used with JSTAC. So JSTAC shell is a bit different. You can encrypt data with ASCII4, and you can also compress it. And now, since all the data is completely encrypted, you'll see a very nice correlation at the beginning of the image too that you can test. Well, for JP-hide, this is slightly different. I had some difficulties at first to figure out how to detect that. So it's a command line interface available for Unix and a slightly more sophisticated version for Windows. And these T coefficients are selected by a fixed table. And this fixed table takes coefficients that are numerically high groups. Because the author figured these numerically high coefficients would have, they would vary more in their statistical bits. And everything is encrypted with blowfish. We'll see that we can detect this very easily. And then finally, outguess, which is this program that I wrote. The DCT coefficients are selected by a pseudorandom number generator that's keyed with a passphrase and also with an image-specific seed. And everything is ASCII4 encrypted. And for this, you need to be a slightly more sophisticated. You have to look at certain parts of the image separately and do the chi-square test. And then you can sort of see how many spikes you get, and you can use that to determine if something is wrong. Well, so now at first I asked this question, how to detect steganographic content automatically? And the answer is StackDetect. That's a tool that I wrote to automatically analyze data images for steganographic content. And to detect JSTAC and JP-hide and outguess. And it's a very easy to use tool. You just run on a bunch of data and you get an output that immediately tells you what to expect. So this image here has outguess with a very high probability. This image here has some JP-hide and sort of lower certainty that they're using. So how does the JSTAC detection work? Well, as you saw in the images, it's pretty simple, and best bet and Fitzman already talked about that. For JP-hide, we have to rearrange the DCT coefficients according to that table, so that we get the modifications nicely lined up. And then we also ignore modifications to the 1, 0, and -1 coefficient, because these are slightly different, and they sort of spread the changes out in such a way that you can't immediately detect that something has been changed there. Because the 0 coefficient is so high in frequency, this test isn't perfect. And then we also ignore modifications that are not released. And that works. But outguess detection was a bit more difficult, because everything is spread out with this pseudorandom number generator. So we have to apply a sliding chi-square test, I call it, where you slide the sample range across the image. And you also adapt the sample size slightly to prevent false positives or false negatives. And the sample size adaptation can also be used to improve the accuracy for JSTAC and JP-hide. And to speed things up, you can stop the test for JSTAC and JP-hide once the probability sinks below a certain threshold, because everything's done from the beginning. And for outguess, you can tweak it by ignoring certain combinations of coefficients with the test. So on my 300 megahertz Celeron, you get about 400 kilobyte JSTAC per second detection speed. JP-hide is slower, outguess is so and so. All tests together are way slower. This shouldn't really be anything figured out what the reasons. Okay, now that we have answered how to detect steganographic content in images, the question still remains, well, now that we can do that, we need to find all these images that we can test. And I mean, the answer is obvious. You take a web crawler, the web crawler saves JPEG images. Well, you'll be amazed how difficult it is to find a web crawler that saves JPEG images. I couldn't find a single one. So I took existing web crawlers and modified. I tried Lavin, which was supposed to be really fast, but it was pretty ugly. I took the Web Consortium's WebRobot, and this was just wasting memory all over the place, so nothing worked. And in the end, I got my own crawler, which I succinctly named Crawl. And in order to make it simple code, I used a library that I wrote that event for asynchronous authentication, so I don't have to deal with any stuff off that in my code. And I could do it with less than 5,000 lines. And it worked. So now I can download images. And the crawler supports a minimum and maximum image size. That is, you don't want to download all those 5K or 1K images because nobody could hide information there. And you don't want to download those 5 megabyte images since they just still appear in others. And so far, I've downloaded about 2 million images that I got off eBay auctions. Why I did that, I will explain in a moment. The only drawback is that the DNS is synchronous. And since you go to many sites, you quite often block on the DNS hookup. But it's a depth first search, and I cache the DNS requests. So that sort of mitigates it. And the crawler outputs its actions as an out. And that means we can use stack detect as a filter to the output of the crawler. So you just run the crawler, you hide every JPEG image that you receive to stack detect, and then stack detect will say, well, there's content in there, this is not good. And after doing that, I found that about 1% of all images seem to have content hidden by JPEG. And this seems to be quite a lot. So this is an indication that my detector isn't quite optimal yet. And in the next iteration, I'm going to make it more accurate in terms of intent. For outguess, I don't think there's much more that I can do because it's sort of difficult to detect. But my detection rate is there is only 0.1%. It's not about. And JSTAG is very accurate. I only get not that many images.
So this is from 2 million images.
Yes, this is the summary of 2 million images. But you'll find that certain types of images are more likely to show up as messages. So drawings quite often seem to be false positive. And if you look at the graphs, this is for JSTAG, you see that they sort of follow the graphs that I showed earlier, but not quite. So maybe I can tweak the program a bit to throw out these results and make sure that there's at least some more positive correlation. And monotone backgrounds seem often to turn up as outguess images. And for the upper painting, there are only a few very high spikes. So maybe that is something that you could filter out to. For the lower image, I don't know, that just looks like a hidden content. But I couldn't find anything there, why I explain it in the short one. And well, for JPEG height, that's sort of similar. I mean, there are many images, different sizes, and different quality. And since we know everything's encrypted, maybe I can do some optimization to the detector there too. And I mean, since I get 1% JPEG height, that's why I need to concentrate on that. Anyway, so now that I have all these images and so many of them turn out positive, I still don't know if there really hidden content in these images. So, in order to really make sure, I need to do something else. And the obvious solution is, since all these programs work with user-supplied passphrases, there's key the encryption and that key the way that bits are selected, the simple solution would just be to try all kinds of passwords and see if we can actually retrieve hidden content out of these images. So what I did, I wrote a program, stack break, that launches a dictionary attack against the JPEG images that turn up positive with stack attack. And stack attack tells me which system was likely to be used, so I can tell stack break what system it should do the dictionary attack against. And I can do that for JSTAG shell because that uses exception. I can do it for JPEG height and outguess. And for a given key system, we read the header and parts of the content and use that information to see if we get the correct key. Because if you give some random key, every system will give you some kind of content. And you still need to determine if that's good content. So stack break is to guess if the key is correct, and we can do that by looking at the header. So for JP Hide, the Unix version, we get a 64-bit header. 24 bits are used to contain the message line. And 40 bits, and I don't understand why at all, are obtained from encrypting the first 8 TCP coefficients, and that's stored in there. So now if we try a key, we can immediately get 40 bits of certainty if we got the right key. So this he made it really, really easy for dictionary attacks. And no, he doesn't select the bits super randomly anyway, and he uses blowfish encryption, doesn't use. And additionally to these 40 bits, we can also use the message length as another verifier to see if we got the right key. And the blowfish key schedule is emission dependent. Well, the Windows version is a bit more difficult, but nicer to terminal. It's fine. We get a 128-bit header, and since it's a post compression, we get two length fields. So we get 48 bits containing original and compressed length. We get 60 bits that are duplicated for some reason. But then we also get 56 bits of IP. So suddenly we end up with at least 72 bits of certainty, which is certainly enough for a dictionary attack, because I'm not going to try to numbers there. I'm not that many words. But there's one drawback here. The blowfish key schedule depends on the image. And I'll tell you in a moment about the drawback.
Two people, I think.
So, I guess for JSTAC shell, the Windows UI, we use RC4 encryption, and there's a 32-bit footer at the end that tells us what encryption was used. And well, the RC4 encryption is restricted to 40 bits, so there's not much to search. And we get 32-bit certainty because of the restriction is because of US export policies. It's an older program. For outgaze, well, things look different here. We only get a 32-bit header, which contains a 16-bit seed and a 16-bit message length. But all the values are possible. So there's no real good way for the stack break to tell if the key is correct. What I can do is I can allow the seed to be restrained because the program starts using the seed from the beginning. And I can specify a minimum message size. But that still isn't enough. I get many, many, many words that fit these restraints. Additionally, I decided to retrieve some of the message in its encrypted form, just to see if I get a high entropy. So I have an additional check that does entropy checking of the data we receive of the image. But nonetheless, if I take a large dictionary, for every image that I try to break on for outgaze, I find some kind of password. So currently, dictionary attacks against outgaze are not feasible, and I don't think there will be. The other obvious thing that you can do is try to retrieve the whole message and then maybe use the Unix file program to see if it matches it. So, well, let me tell you some about performance, and then we get into the next problem area that I have. My 1200 megahertz Pentium, I get about 15,000 words for JP height. And the first run that I did was 300 images with about 500,000 words, and that took 10 days. Really slow. The problem is that the blowfish key schedule is so expensive. For the Windows version, I can't cache it. Well, I can cache it if I find images that have the first 8 TCP coefficients the same. That's what I do. But still, with only 300 images, it's unlikely that you get many that for which there's. For outgaze, it's a bit faster. I get 47,000 words per second. But with a large dictionary, I find it ended for every word that I try. And JSTAC shell, I get about 100,000 words per second. And since the key space is only 40 bits, the brute force searches entirely feasible. Well, but for JP height, and those are most of the images that I get, stack break is way too slow to be feasible on a single computer. So I faced another problem. I needed some way to distribute these stack break jobs to a bunch of workstations. So I needed a simple distributed computing framework that I could supplement a cluster of loosely coupled computers. Loosely coupled means that the workstations between themselves don't have to communicate. And I wanted it easy to be set up and to maintain because I have to do it myself and I don't bother wasting time on that. It needed to be portable to many operating systems so that I could run it on many machines. I wanted communication security, everything should be encrypted and authenticated. And I also wanted unprivileged execution. And in this case, I don't mean unprivileged execution of the job that I want to run. I mean that I should be able to set up the client without having any privileges. Well, since I couldn't find anything that met these requirements, I had to develop my own program, which I called this. And it uses a little bit for the authentication. But then I faced another problem, to write something which is a bummer. So I wrote a library called the bio that abstracts all communication to data sinks and data sources.
Yes, and you want to come down.
So I can just abstract encryption and authentication away and filter it. And the core of the program doesn't have to do with anything. And so I was able to write such a framework with less than 37 lines, and it works quite nicely. So how does it work? Well, you can set up a job with the init command. The init command transfers files to all selected clients. So in my case, that would be the top file that contains the stack like binary and the word list and stuff like that. And then another top file that contains the data that the job should work with, all my images. And job parameters you can set up with the job command. And finally, you just say, run this job, and it will be sent to all computers. And once the computer finishes, a new parameter will be sent to that computer just in that computer. And this external snapshot that you see there, it was one of the jobs that I run. So the parameter range, 1 to 2,500, is right there. And you have certain arguments that you can send in slots, the current working unit. And it's just a parameter to make it easier for the remote side to determine what workload to work at. And you see statistics. Minimum time for a slot of 3 minutes. Maximum time was almost 2 days. And this has been running for 5 days already. There was over 3,000 images with workers that was about 1 million words. Well, it took about 7 days to complete. In order to get feedback from the client side, send it out and send an error and redirect it to the server. And both server and clients can deal gracefully with connectivity logics, maybe temporary function. If they are temporary, the client will just reclaim the job appeared if they are permanent, the server will just restore. And most of the jobs can run this. Well, now that I have this great framework, there still remains one difficulty. How do I find all these machines to run the client on? And so one night, while being in Boston, the field produced defaults, and after a couple of years, we should never forget them. I decided to make use of the vast resources of the University of Michigan. And so I started hundreds of these clients on various workstations on the campus. And when I started my job and everything was blazingly fast, I was very happy. I was not that happy when the next morning I received this email. We detected massive background computing jobs from your account. If you don't stop immediately, you will lose all your computing privileges. And so I said, bummer. I mean, it was the holidays, not many people were around, but these people are very sharp. So in the end, I asked them nicely if I could please use their computers, and I was permitted to use 50 machines at a time. And so a normal stack break job runs on 60 machines, 10 CT and 50 on campus. And stack break itself is really low I/O and low memory requirements. So it's and on my desktop I can do 12,000, so this is about 15 times faster. And clients vary in their performance, and these are some statistics on some of the jobs. So our clients only do 500 words per second, which is a lot slow. So maybe I should tweak my framework to test computer performance before I start jobs. The average time was 4,000 words per second, and the maximum was 12,000. That was my guess. So far I've downloaded 2 million images from eBay. I immediately found problems with the crawler directories that travels to more than 30,768 entries. And I found about 17,000 positive images. 15,000 of these
JPEG. Well, even with my distributed framework, stack rate is still vector slow. So it can't keep up with all the images that I find. And so I need more and faster clients to deal with that issue. And unfortunately, even though I've done this for a couple of months now, so far I was not able to find a single genuine hidden message, which is unfortunate, but all these jobs always find the messages that I put in, which is good. And I hope that in the future I will be able to answer the question if there's really hidden content on the internet. The popular press claimed that images were on eBay, Amazon, and pornographic bulletin boards. So far I've only tried the eBay venue. Well, that seemed promising to me because eBay, at least from its traffic characteristics, would be an ideal place to use steganography. I mean, thousands of people are putting images up all the time. Thousands of people are looking at these images. So just by looking at the traffic patterns, it should be hard for anybody to tell if some secret communications. But for my future work, I should get images from different sources, maybe Usenet. And of course, as I told you, I need to refine stack detect to be more accurate, and I need to find more computers to run the breaking job. So in conclusion, I developed new techniques and tools to find hidden messages on the internet. I developed stack detect, which automatically detects via statistical means that stack another content has been hidden. I wrote crawl to get me all the images. I wrote stack break to do dictionary attacks against different stack another systems. And finally, I developed disconcert, this distributed computing framework. All the software is available on BSD license. I yet have to release stack break and disconcert, but I should have soon. You can find the software on my homepage. And Outgate's version 2.02 is undetectable by these techniques. So if you find yourself in desire need package content, recommend it. So that's my talk. If you have any questions, I'll be glad to answer. Yes.
Since all digital content currently is covered by copyright, and you're developing technical means to reveal copyrighted information that has been hidden, are you concerned that you might end up talking to us through iron bars when you return to the US?
So Dr. Honeyman is asking, since all digital content is covered by some copyright of some sort, and the systems that I use sort of have with copyright protection, and I'm trying to supplement that, do I have some concern that my academic research will get me into jail in the United States? And actually, yeah, I do have some concern about that. I just recently improved stack detect to find invisible secrets, which are commercial products, and their ingenious scheme to hide content in a JPEG image is to put the content like it is in a JPEG comment field. And for the fact that with the DMCA, apparently you can get to jail anytime. Yes, I'm really concerned about that, so I don't know what to do about it. I hope it's being straight. Do we have other questions? Yes.
You see that the kind of break between someone breaking the code, someone hiding information from some message or something. The one who is hiding information always wins because he can dilute this information so strongly that he can adapt the statistical properties of that information to this image is used.
So the question is, there seems to be an arms race here between the people that make systems and between the people that break them. And that's entirely true. And I think that my steganographic detector is an encouragement for people to make better systems. And that's what I tried to do with my improved outgates, because I developed techniques to confound these frequency count-based statistical analysis. Yes, so that, sure. I mean, the moment you break something, somebody else will unbreak it.
So the market follows that the only thing you can use to detect the message is statistical analysis. My market that if you are able to find a scheme which adapts your hidden message in a statistical way to your original image,
So
if it goes forever.
Yeah, if I can find a way to adapt my hidden message to statistical properties, then statistical analysis will not be able to find it. And that's true. However, it's not publicly known what statistical properties there exist. So if you identify some, somebody else might identify others. So we have time for one more question. Yes. So he is saying in the statistical analysis phase, I have different phases to determine which system hits the information. Yeah, that's absolutely true. I mean, for every program, I do a different test to determine if it's true. So sometimes you'll find that state detect tells you, well, there's outguess in there, and there's JP height in there too. So, yeah, that's true. So I think we're done. Thank you very much.